It's my pleasure to introduce the last of our speakers for the morning session, and this is Paul Knochel. And he was born in Strasbourg, France in 1955 and did his undergraduate work at the University of Strasbourg there, graduating in 1979. He then completed his PhD at the ETH Zurich with Professor Peter Seebach. After 4 years at the CNRS at the University of Pierre and Marie Curie in Paris under Professor Normand, he also then did a one-year postdoc at Princeton with Semohac. He then, as a lot of incredible chemists do, he passed through the University of Michigan in Ann Arbor, go blue, at least temporarily, in 1987 as an assistant professor, and then was promoted to full professor in 1992. From there, he moved back to Europe to Philipps University at Marburg in Germany from 1992 to 1999, and then he moved to the chemistry department at Ludwig Maximilians University in München, Germany. Dr. Knochel's research, as you know, focuses on organometallic reagents, and there have been many times in designing syntheses I've come upon his papers and they've saved the day, so I thank you for that. And his title today will be Functionalized Organometallics in Organic Synthesis, very piquing my curiosity.
Thank you very much for your introduction. I would also like to thank Scott for inviting me to come to this fantastic meeting. I learned so much chemistry in the last days, and especially the evening talk of Dave. Not only the chemistry was important, but the philosophy behind the chemistry, so it was very, very stimulating until now. So today I would like to tell you something about the preparation of polyfunctional organometallics. So we try to have in the same molecule the usual functional groups that you meet in organic chemistry and a reactive carbon-metal bond. And it turns out that the metals, which are very good for making such reagent are magnesium and zinc. They have very excellent chemoselectivity, low toxicity, and a low cost. I would not say they cost just a few cents, but not much more. How can you prepare such organometallics? The simplest reaction is an insertion into a carbon halide bond. And when you look at the preparation of, for example, adamantyl zinc reagent, there were some preparation of the magnesium intermediate. There was a preparation of adamantyl zinc by using the method of Rieke, preparing activated zinc. But when you prepare activated zinc, you have lithium chloride present, and you can, by refluxing with this bromide, make the zinc reagent. It turns out that what is important for activating a metal is not only the small particle size of the metal, but just the presence of lithium chloride. So it means that if you take just adamantyl bromide, magnesium powder, not specially activated, but you add lithium chloride, you have a very fast insertion of magnesium and then transmetallation to zinc, and you can form this zinc reagent in a very simple way, 85% yield, and then you can use it for making cross-coupling reaction. There are a number of interesting pharmaceuticals which contain an adamantyl rest, and this method is a very simple way to introduce this bulky tertiary group. Now, the direct insertion reaction has a lot of interesting properties. First of all, it is very regioselective. So, for example, if you have a diiodide and you treat it with zinc and lithium chloride, you just observe the insertion of zinc into the more activated carbon iodide bond. It means the most electron poor carbon iodide bond, and you form just this zinc reagent. And then you can, of course, add a little bit of copper cyanide, transmit it to copper, and perform, for example, acylation. But also, this zinc insertion is compatible with many sensitive functionality, even aldehyde group. And here you see an unsaturated, beta-bromo unsaturated aldehyde that you treat with zinc and lithium chloride. But you know, the effect of the lithium chloride is to clean up the surface of the zinc, and once the organozinc compound is formed at the surface, it complexes with the lithium chloride and is then solubilized in the solution, and so you have the active side of the metal which is ready for a further insertion. So this is, in our opinion, the effect of lithium chloride. So you can make a zinc compound with an aldehyde function and then, for example, perform a cross-coupling reaction. And the last property of this insertion, it can be stereoselective, although it's a one electron transfer reaction that you have first formation of a radical and then transfer of a second electron, but because of the complexation with the carbonyl group, you just form one organozinc compound, and then you can again perform Negishi cross-coupling with retention of the stereochemistry, and you get this compound in good yield and almost perfect control of the stereochemistry of the double bond. Now, so zinc compounds are easy to prepare, tolerate many functional groups, but they have the problem that they are sensitive to water and sensitive to oxygen. And our question was, is it possible to prepare such organometallics which are much more compatible with oxygen and with water? And what we did is that we prepared again such zinc reagent by using magnesium instead of zinc as reducing reagent, because magnesium is a stronger reducing agent, so you make magnesium compound in the presence of zinc chloride and you get in fact a zinc reagent. Or you do a direct CH activation of a hydrogen with a sterically hindered base. I will tell you more details about this type of reaction. But then we treated this zinc and magnesium reagent with zinc pivalate and made a zinc reagent where we have replaced the halide with a pivaluloxy group, and because of this extra coordination of the carboxylate to zinc, we were hoping that the zinc reagent that you obtain would have a good or improved air and water stability. And this is in fact the case. I will show you data in 2 slides. But first, let's have a look on the preparation. You just need to take aromatic or heterocyclic or benzylic bromide or even chloride in the case of the benzylic system, add magnesium, zinc pivalate to lithium chloride, and this system, the zinc salt, the zinc pivalate and the lithium chloride activates the magnesium surface so that the insertion is complete at room temperature within 20 minutes to 2 hours maximum, and you get the organozinc compound with function present like a cyano group or even ester function, and you obtain all this aromatic or heterocyclic zinc compound in acceptable yield. The second method for making this organozinc pivalate, which is even more effective and proceeds in even better yields, is the direct metallation of aromatic or heterocyclic system with TMP, magnesium chloride, lithium chloride. Tetramethyl piperidine, magnesium chloride, lithium chloride. And the metallation proceeds at almost ambient temperature, or at least in Munich, 0 degree. And you get after addition of zinc pivalate, the organozinc compound, you see the yields are good. You can use heterocyclic systems. And when you take these zinc pivalates and you use them in Negishi cross coupling, you see that the reaction proceeds in quite good yield. The catalyst that we use here is the Pepsi palladium complex from Mike Organ. Here the trisortophoryl phosphine from Vittorio Farina. The reaction are proceeding very well, especially zinc reagent or organometallics in alpha position to pyridines have the reputation of proceeding, undergoing cross-coupling under relatively harsh conditions, but you see here it works quite well. And here a last example where we add BF3 to control the regioselectivity of the metallation, and you see that the cross-coupling is also going very well. Now, what is the air stability of this zinc reagent? Here you have a collection of aromatic heterocyclic solid zinc compound that we made after evaporation of the solvent. And you see that when you titrate them after 1 hour on air, you see that you have almost no change. After 2 hours, you have still 99% of the zinc reagent. And even after 4 hours, you have still 4 hours just on the bench of your zinc reagent, you have still 90%, 84, 86, 98 in this case. So that you can use this reagent, not like they're not as stable as boronic acids or boronic esters, but they have much improved stability, and organozinc compound in contrast to boronic esters transmetallate much faster to palladium or other transition metals. Now, let me show you one of the advantages of this using this solid zinc compound. First of all, you can do cross-coupling with systems which contain acidic proton, like a proton of an amide, room temperature 2 hours with the 2% of the Pepsi catalyst, you get the cross-coupling product in 87% yield. But also, you see, in this cross-coupling with chloropyridine, you can choose the solvent for your cross-coupling, and whereas with THF you get a yield of 84%, just changing THF to ethyl acetate now leads you to a yield of almost quantitative of 96%. So you can prepare, convert a number of heterocyclic system very simply just by treatment, by metallation, transmetallation, evaporation of the solvent into a zinc reagent, and after you see the air stability of this reagent is quite good. You get a yield in this sequence of 98%, and then you leave it 1 hour on air, and you have still 97% of this 98%, and then you can do a cross coupling. This cross coupling, you can of course perform it with extra dry THF under argon. Yield is 86%, but you can also use technical grade THF and work on air, and you see the the drop in yield is not very important. This means that this reagent are quite robust for application in cross-couplings. And you can use more bio-relevant heterocycle, metallate, for example, this purine, get the zinc compound. It has also a good air stability and do the cross-coupling reaction. Now, it is also possible to take the TMP magnesium chloride, the base, and combine it directly with zinc pivalate to make a TMP zinc pivalate, and this is an excellent base which metallates, for example, this pyrimidine at position 5, and you get just this zinc compound. And not only has this reagent as a solid, excellent stability, but it gives cross-coupling in good yield, but also you can, just by changing the catalyst, adding copper cyanide to lithium chloride, you can do acylation reaction. And what is important is that this zinc base is compatible with the presence of many functional groups. Here you have an aromatic system with a nitro group, and you get only a metallation in this meta position. The two other positions are not metallated at all. You get at room temperature in 45 minutes, you have the formation of this functionalized aryl zinc reagent, and then you can do an efficient cross-coupling. Here you have another system. You see, this is a furane. Furanes are easy to metallate in position 2 or 5, but metallation in position 3 or 4 are much more difficult. But because of the sterically hindered nitrogen amide, here you have a monomeric species which is quite efficient for making metallation. And so you get a metallation not in the most not from the most acidic hydrogen alpha to or beta to the nitro group, but you get a metallation of this hydrogen beta to the ester function. Why? Because the TMP zinc base coordinates to this ester function, and this directs the metallation at this position. The selectivity is excellent, and then after you can do, for example, in the presence of a little bit of copper cyanide to lithium chloride, you get an allylation in this position. Here is a chromone that is selectively metallated also at this position, and then acylated in good yield. Now, it's interesting to see the selectivity of the reagent of this zinc pivalate. They contain, because of their preparation, magnesium salt. And because of this magnesium salt, they are reactive with for example, an aromatic aldehyde which contain a bromide. Yeah? So you get an addition to the carbonyl group, and you obtain this secondary alcohol. With a ketone, a chloroketone, you get with this benzylic zinc compound an addition to the carbonyl group because of this magnesium salt which were present, which play the role of a catalyst and favor the addition reaction, so you get a tertiary alcohol. On the other hand, if you take the same zinc reagent with the same electrophile, but now you add a palladium catalyst, like Pepsi, then you get a preferential cross-coupling with this carbon-bromine bond or with this carbon-chlorine bond, and you obtain the alternative cross-coupling product. Now, let me tell you also something about this sterically hindered base solubilized by lithium chloride, because you have a bulky amide, you have a monomeric magnesium reagent, and this the solubility of this monomeric magnesium chloride in THF is improved by adding lithium chloride. You can make a number of bases like this with aluminum, manganese, iron, and lanthanum, and so on, and prepare the corresponding aryl or heteroaryl organometallics. But I want just to show you today a few applications of this base, which is quite active. It's prepared very simply just by taking TMPH and adding isopropyl magnesium chloride, lithium chloride. You get a molecule of this type where you have the two metals, magnesium and lithium, present in the monomeric species. There is a X-ray structure of this species which has been elucidated by Robert Mulvey. And if you take this compound, now it's possible to make metallation, selective metallation of aromatic system which contain many functions. Sensitive function like a Bock group, a keto group, two ester groups, and you see you have two hydrogen, and TMP magnesium chloride just abstracts one hydrogen to prepare the Grignard compound. So you can make functionalized aromatic or heterocyclic, we will see, a Grignard reagent. If you would like to do a lithiation, a directed lithiation of this aromatic system, you would never have the possibility of tolerating ester groups or for example, a Bock functionality, because the aryl lithium that you generate would attack these functions. So the magnesium compound, after transmetallation with copper cyanide, can, for example, be acylate very easily. Now, the metallation condition using TMP magnesium chloride, lithium chloride, are usually quite nice. You don't need to cool to minus 78 degrees like directed lithiation. Here, for example, we had some aminopyridines that we protected the amino function with a trifluoromethyl group and carbonyl group, and then it is possible to do a metallation in 5 hours at room temperature. The metallation proceeds selectively at position 4, and then you can perform an allylation reaction. If you have a chlorine present, it doesn't change anything, and you get a very efficient cross-coupling after transmetallation with zinc. Also, this pyrazine is metallated in the ortho position to the amino function. You can do a cross-coupling and remove the trifluoromethyl acetyl group just simply with potassium carbonate, and you get the free amino pyrazine. Now, zinc and magnesium compound, they are also compatible not only with a lot of functional groups, organic functional groups, but also compatible with Lewis acids. And so, for example, if you if you want to perform an addition of an organometallic to a carbonyl group, the metal plays also the role of a Lewis acid, coordinates to the carbonyl group, and then you have activation of this carbonyl group through the metal, and this facilitates the addition. But you can also imagine a dual catalysis where you have not only an additional acid, Lewis acid present, but also a Lewis base. So the Lewis acid would activate the carbonyl group. The Lewis base could activate the organometallic reagent and make it make the R group more nucleophilic, and this facilitates the addition, and you get this addition product in much better yield. This is possible when the Lewis acid and the Lewis base are not reacting with each other, or if they react, they have to react in a reversible way. Now, this is a kind of situation that you observe when you have frustrated base pairs. There is a very nice example of the application of frustrated Lewis pairs. This means when you have molecules where you have a basic center and an acidic center, but they cannot cancel each other, react with each other. And for example, with this molecule, Stefan has shown that it's possible to activate hydrogen and split hydrogen at room temperature. So using this dual catalysis is possible with a number of magnesium and zinc reagents. For example, it is possible with the TMP magnesium chloride base and BF3, which is a strong Lewis acid. Both of these reagents, if you keep them below minus 20 degrees, maybe they react with each other, but this reaction is reversible. And so if you add a substrate like pyridine to the mixture of these two species, then the BF3 coordinates the nitrogen, and the base will easily deprotonate this hydrogen to give a magnesium reagent, which then is converted to a boron species when this is shown if you look the NMR of the final product. Now, by using this methodology, you can, if you have 3 substituted pyridines, you can, with TMP magnesium chloride, make a selective metallation, for example, in position 2. But if you add BF3, the BF3 blocks this alpha position, and the TMP magnesium chloride is now able to abstract hydrogen in position 4. BF3 acidifies all the position, and for this reason, this position 4 is easily deprotonated with TMP magnesium chloride, lithium chloride. So for example, you can, with BF3 and then adding an aryl iodide with palladium catalyst, you can do an arylation in position 4. In the absence of BF3, you will do an arylation in position 2. This is a quite general phenomenon. So you can take a number of substituted pyridines with cyano group, with bromide and cyano group, with ester function. And if you add BF3, you get, you block the position 2 or 6, and you favor the metallation in position 4. Here, you block these 2 positions and you favor the metallation in position 5, metallation in position 4. But if you do not add BF3, then you have metallation in position 2 in these 2 cases. In the last case, if you take this molecule and add TMP magnesium chloride, lithium chloride, you get no product because the metallated product in position 2 is just a magnesium reagent, is too reactive and undergoes polymerization or Chichibabin type reaction. You can extend this approach to the functionalization of quite complex molecules like quinine. You take this molecule, deprotonate the alcohol function, complex it with BF3, and finally, when you add TMP magnesium chloride, you metallate in position 3, and you can do an hydrolysis, bromination, or directly a cross-coupling reaction. So this type of approach, you can use it to functionalize completely selectively the pyrazine heterocyclic system. So if you use an equivalent of a methylpyrazine, which is this pyrazine containing methyl substituted with 2 TMS group, which is very simply prepared by a Kumada cross-coupling reaction. This reagent, then, if you treat it with BF3 and you add bis TMP magnesium chloride, you get a selective metallation at this position, this para position to the bis 3-methylsilyl methyl group. Why is this? The BF3 will coordinate the least sterically hindered amino group, activate the position in alpha and alpha prime, and then you need a quite strong base to do a deprotonation. This is simply bis TMP magnesium 2 lithium chloride that you obtain by taking TMP magnesium chloride, lithium chloride, and adding TMP lithium. This base deprotonates then selectively in this position. And then you can do, for example, an iodolysis, or you can chlorinate, brominate, do cross-coupling in quite good yields. Now, once you have introduced this first electrophile, you can metallate again with bis TMP magnesium, and the only position which is available, easily available, is this one, now in meta position to this bis 3-methyl methyl group, and you can then introduce again a number of groups by reacting just with iodine, bromine, or bromine equivalent, NBS, or you can do an allylation, arylation, and so by when you have made this functionalization, the last position can again be deprotonated with bis TMP magnesium, and you can, for example, allylate, or here you can make iodolysis. So depending on the order that you use for introducing your substituent, you can make the two isomeric compound with very good selectivity, complete selectivity. Now, once you have prepared this tetra substituted or substituted pyrazines, you can convert this bis 3-methylsilyl methyl group, for example, in a methyl group just by adding TBEF, but you can also perform a Peterson olefination reaction, or you can treat it with CAN and form the corresponding aldehyde also in good yield. You can also use this substrate and treat them with an amidine of this type and form the corresponding heterocyclic compound according to a method recently described by you. Now, this compatibility of magnesium reagent with BF3 can be extended also to a compatibility with triethyl aluminum. And why is this interesting? Because a few years ago we have reported some aluminum bases, tris TMP aluminum, or this very sterically hindered aluminum species, and they are excellent for performing metallation of systems which are electron rich. Containing, for example, methoxy groups, you can do the very selective metallation, which are not possible with the TMP magnesium chlorides. Unfortunately, it turns out that these bases, they react, if you have no substrate, they react with THF, you have a deprotonation, fragmentation of the THF which occur, and so these bases are not stable for a long time at room temperature. You can solve this problem just by making this base in situ. It means that you take aromatic substrate, you add triethyl aluminum and TMP magnesium chloride, and so you get a relatively fast metallation. You form an aluminate species, and then you can, for example, treat this aluminate species with an aldehyde and get the addition product. You can also perform allylation reaction. So for example, if you have this complex aromatic with 2 oxygen function, adding just at 0 degree triethylaluminum and TMP magnesium chloride, you metallate selectively in this position, and then you can do an allylation. If you add zinc pivalate, turns out that the addition of zinc pivalate improves greatly the yield in the subsequent allylation reaction and subsequent cross-coupling. The next slide shows you again a few examples, a few metallation reaction using this cyano-substituted methoxy group. Here the cyano group is the directing group, so you metallate in alpha position and you get the cross-coupling product in good yield. Also, the last example shows you here that by using triethylaluminum and TMP magnesium chloride, you can metallate this system, and the corresponding aluminum compound directly gives oxidative coupling. If you add chloranil at minus 78 degrees, you get the carbon-carbon bond formation in 73% yield, and this molecule is then a precursor of difluorophos, which is a chiral ligand used for asymmetric catalysis. Now, this selectivity in the presence or in the absence of Lewis acid is not only possible with N-heterocycles, but also with oxygenated heterocyclic system, like for example the chromone system. So if you take chromone and you treat it with TMP, zinc chloride, lithium chloride, so it's just a zinc amide. And usually zinc amides are not very reactive for deprotonation because they are aggregated. But here, because of the steric hindrance and the addition of lithium chloride, you have a quite good reactivity, and at room temperature in 15 minutes you deprotonate, and you deprotonate in position 3 selectively. And you can then do iodolysis, acylation, arylation, allylation. And it turns out that if you replace TMP zinc chloride with bis TMP zinc, then the position of metallation changes. You do not metallate again in position 3, but only in position 2. And you can again acylate, arylate with reasonable yields. So why do you get this why do you observe this difference? And it turns out that it's quite easy to explain, because the TMP zinc chloride complexes, of course, with the chromone system at the carbonyl group. This is a quite electron-rich carbonyl group. It complexes at this position, and then the amide moiety will just deprotonate this hydrogen in position 3. On the other hand, the bis TMP zinc that you use has been prepared from TMP, magnesium chloride, and addition of zinc chloride. So you have magnesium salt present. And the magnesium salt complexes the oxygen. So a deprotonation of this hydrogen in alpha position is no more possible. The TMP, the bis TMP zinc complexes then to the second oxygen and then deprotonates now in position 2. So how, it looks good, it's a nice story, but how do we, can we prove this type of mechanism? And so what we did is we took the TMP zinc chloride, which directs usually in position 3, and we added BF3. It turns out that now, in the presence of a Lewis acid, not magnesium chloride, but BF3, now you change the regioselectivity. The TMP zinc chloride does not metallate anymore in position 3, but in position 2. And you can do, for example, allylation, iodolysis, and other reaction under this condition. This is true not only for chromones, but for quinolones, for the corresponding thiochromones, you observe the same kind of reactivity. And there are also other systems which give exactly have the same behavior, like for example uracils. And here we have made this uridine system, and treated it with TMP, magnesium chloride, lithium chloride. If you do this, you metallate in position 3. On the other hand, if you use the bis TMP zinc with two equivalent of magnesium chloride, which are present due to the preparation of this base, then you get metallation at this position 2 to the nitrogen, and you see you can prepare the corresponding 3 substituted uridines or 2 substituted uridines without any problem in good yield by using this method. Now, not only zinc bases or zinc or magnesium bases are compatible with BF3, but also the magnesium reagent themselves and the zinc reagent. Zinc reagent react with BF3 only at room temperature. Even at 0 degree, the reaction is very slow. And you can verify this very easily by doing hydrolysis and quenching with H2O2. So you can differentiate if you have still a carbon-zinc bond present or a carbon-boron bond which would be obtained by reaction with BF3. And so you can use this method to functionalize the pyridines, to react pyridines with nucleophiles. The reaction of pyridines and acyl pyridines with nucleophile is well known, and especially André Charette, Crimins have shown that if you make acyl pyridines, you get a reaction at position 2 or 6. It turns out that when you use this method with BF3, you can add Grignard reagent, like isopropyl magnesium chloride, lithium chloride, you can add it at position 4. Then, at the end of your reaction, you just add chloranil, which is an excellent redox reagent, oxidant, which allows a redox system to take place, and you get the substituted pyridine in position 4 with good yield. So you can introduce a number of groups, cyclohexyl, octyl groups. The selectivity is perfect in the case of these pyridines. You don't need to have a chlorine at this position. You can have a phenyl group, you can have a vinyl group. You can also perform this synthesis with pyrimidines. If you use a quinoline and you introduce this isopropyl group, you get 95% in position 4 and less than 5% in position 2. This is one of the few cases where we observe a mixture of regioisomers. So this sequence allows you to perform a cross-coupling, if you want, without any transition method. The reaction can be extended to benzylic system. So you can take a benzylic zinc compound containing magnesium chloride. Very simple to prepare because you just take a benzylic chloride that you treat with zinc chloride in the presence of magnesium powder or magnesium turning, and you get in very high yield in short time the benzylic zinc reagent. I have to say this is a fantastic method for making benzylic organometallics because again it tolerates a number of functions, cyano groups, ester groups, even keto groups. And it's not possible, for example, to prepare a benzylic magnesium reagent with any of this function because the carbon magnesium bond of a benzylic system is so reactive that it reacts with all this function. This is not the case for the zinc reagent, and so you can do addition in position 4, which proceed quite well. Now, what about if you want to add functionalized zinc reagent? Like, for example, this acetoxy-butyl group. The way you do it, you just take a zinc compound and you add tertiary butyl magnesium chloride. You make a mixed zinc reagent with an octyl group and a tertiary-butyl group, and it turns out that the octyl group is transferred preferentially and that the tertiary-butyl group is not transferred. And so you can make the octyl substituted system in 90%. If you have a cyano substituent, you have 99. And here we took a zinc reagent with acetoxy group and introduced it in position 4 with 93%. So this kind of cross-couplings without palladium or without nickel can be made also, you see, starting with an iodide. You add isopropyl magnesium chloride lithium iodide. In a few minutes, you make the magnesium compound, and this magnesium compound then adds to the pyridine. After addition of chloranil, you get the cross-coupling product. And the method using magnesium and lithium chloride for making the magnesium reagent is quite efficient. You can use a bis iodide, make the bis magnesium compound, and then do the bis cross-coupling reaction in one pot, and you get this product in 40%. So, of course, it is good to do cross-coupling in the absence of palladium, which is still somewhat expensive. But we tried, because we were quite interested, for collaboration with industry, to make cross-coupling with various pyridines, cross-coupling, sp2 cross-couplings of aromatic organometallics with pyridine electrophile and related systems. And for this reason, we looked at the use of metals which are very ecologically friendly, like, for example, iron. And it turns out, ironically, that if you want to do a cross-coupling between a magnesium organometallic and an aryl halide in the presence of iron, you get a lot of homocoupling product. This is quite disturbing. You can solve this problem by transmetallating the magnesium compound to the copper compound, and then if you do the cross-coupling, it works, the yield is good, and you have much less homocoupling product. But this is not so good, because you have now stoichiometric amount of copper salts. Copper is not expensive, but ecologically it's not the best thing to do. So we were looking at other possibilities. Alois Fürstner has reported a cross-coupling of chloroguanolene with phenylmagnesium chloride. There were some reports from Japan, from the University of Kyoto, from Nakamura, by using this carbene ligand. What we did a little search, and it turns out that if you take functionalized Grignard compounds and you do a cross-coupling with 3% of iron bromide in a solvent which is not so polar, if you add just to the THF tertiary-butyl methyl ether and you use a 1:2 mixture, you get the cross-coupling product. It works very well, but it works quite well, but there is a difference depending on the substrate. The compound that we really want to couple are pyridines, substituted pyridines, but it turns out that when you use a quinoline, you see the reaction time is 5 minutes, and when you use pyridines, especially chloropyridines, you have 2 hours reaction time, and here 1 hour. Here I show you the system which works very, very well. But in some cases, depending on the substituent that you have on your pyridine, then the cross-coupling is not 1 hour or 2 hours, it's 24 hours. And even the completion, you never go to completion. If you add more iron, you add more Grignard, it doesn't change the situation. So we were surprised about this difference, and Andy Steiber, a graduate student, was suggesting that maybe the quinoline or the isoquinoline that you use, chloroquinoline, may be a ligand for the iron and catalyze the reaction. So we tested this, and so we took a chloropyridine, added phenyl magnesium chloride in the presence of an additive. You see, and we left just the reaction 15 minutes. And it turns out that without additive, the reaction leads only to 40% of product, but with additive like quinoline or isoquinoline, now the yield is much enhanced. And so it turns out that if you take, for example, this chloropyrimidine, and you do the cross-coupling without any ligand, 2 hours, after 2 hours you get 76% yield. But if you just add 7%, you could add 6, it would be similar, or even 3 or 5. But we use, for some reason, 7. 7%. After 5 minutes, you have 89% yield. And this method, although it's still not perfect, we are still looking for finding more substituted, more appropriate ligands who would facilitate this cross-coupling. Now you can take a relatively substituted system with a bromine, a fluorine, a chlorine, and it's only the bromine which gives the cross-coupling reaction. The reaction is fast, to 25 degrees now 10 minutes, and you see without isoquinoline, for example, your yield is only 43%. And even if you leave it longer, it doesn't improve the yield. No, it just, the reaction stops, there is a decomposition. And what we found also is that this reaction is not only possible with iron bromide, but also with cobalt dichloride. And here you see without isoquinoline you have 10%, with the isoquinoline you isolate 71%. And here are a number of other cross-coupling reaction. Here, it's really a cross-coupling between an heterocyclic system and with another heterocyclic system. And this is something that we wanted to do, is a collaboration with Novartis in Switzerland. Now, the one reaction I have not showed to you, and this reaction is the bromine magnesium exchange. And I want just to show you that this is a wonderful reaction which tolerates many functionality. So even if in your molecule you would have a peroxide, this peroxide would be absolutely tolerated. You take just the bromide, you add isopropyl magnesium chloride, and you form the magnesium compound. Here we use this enamine, and it turns out that with this enamine you get a very nice exchange. You make a Grignard compound, the enamine function doesn't care, but then you add copper cyanide to lithium chloride, 30% or a little bit more, 100%, it depends, and you get intramolecular carbocupration, which leads to this magnesium compound. Then you can quench the magnesium compound with an electrophile, you get all these products. And the TMS group, you can convert, you just add ICl and you have iodide, and then you can do another functionalization. I don't want to show you this because Peter Wipp showed a few days ago some beautiful indole synthesis, so I don't want to show you one more. I want just to show you that because of this tolerance of functional groups, this is a very powerful method for making rings. And you can make rings not only with an aryl ring as this scaffold, but you can use also heterocyclic system. And so you can use the same method, for example, to make azaindoles. So you can make 7 azaindoles, 5, 6, 4. I will show you it's very simple. You just take commercially available material, you make the sulfonamide, you deprotonate, you add this iodonium compound, very simple to make, and you get this compound. These enamines are stable, very easy to handle, air stable, no problem at room temperature, and you can make again the bromine magnesium exchange, then you do ring closure, and you can quench them with electrophile. So let me just show you the last example of this series is that you can make a system of this type, make this bromo enamine. And you see, this bromoenamine, you can either make a 4-azindol simply by making a bromine magnesium exchange, adding copper and closing, then you get this compound. But you can also add magnesium chloride to activate the nitrogen, and then TNP lithium to metallate at this position, and this time you get the ring closure in the other direction, and you get a 6-azindol. So this methodology is quite versatile, and you can make a number of different diaza indole. We are just working using pyrimidines as substrate, and the results are quite promising. The very last thing that I would like to show you is that I noticed that you will have the impression that what we do in Munich is really flat chemistry because we have no stereocenters. And just in a few slides, I would like to show you a reaction that we have studied. It's more fundamental in the sense that the conditions are really below room temperature, even in Munich, you see, minus 100 degrees. And our question was, is it possible to do iodine-lithium exchange, not on an aromatic system, not on an heterocyclic system, but on a secondary alkyl? Bill Bailey and Negishi also had shown that a primary system with primary iodide, it is possible to do this iodine-lithium exchange reaction. And our question was, is it possible to extend it to secondary system? To make a secondary lithium compound with R1 and R2, this time contain no oxygen, no nitrogen, we can chelate, but just a regular chain. And the question was also, is it possible to generate this reaction, to use them, or do we have problem of configurational stability? There was not so much known on this secondary system because they were difficult to synthesize. And so when we used the condition developed by Bailey on this iodide, cis tertiary iodide, well, it did not work very well. We got 4% yield. This is the problem. This is the problem because when you generate this lithium reagent is as reactive as tertiobutylithium. Even if you add 2 equivalents of tertiobutylithium, the secondary lithium compound, especially if it is axial, just does a deprotonation, and then you kill your lithium reagent and you get just a protonated species. Another problem is that this lithium species can also just undergo elimination reaction with the substrate, and then you have just this product, and this makes that your yield is 4%. This is a yield which is desperating. Yeah? So what can you do? My student, she was thinking that the problem comes because you add your tertiobutylithium to the iodide, and this is the reason you have a lot of the lithium species and only a little of the tertiobutylithium, and this is why all these side reactions are done not by tertiobutylithium but by the secondary lithium compound, which is also very reactive. And so what we did, we changed the order of addition. We put the tertiobutylithium in the pot and added the secondary lithium compound, and then it's good. You know, you can make the lithium compound. If you start with the cis compound, you make the cis compound. If you start with the trans compound, you make the trans compound. But both do not have the same stability. The cis lithium compound, within 7 hours at minus 100 degrees, completely isomerizes to the trans. Which is much more stable. Why is the trans more stable? Because the solvatation of the trans is much easier than the solvatation with ether of this cis cis lithium compound. You see the carbon lithium bond is axial, and if you put THF or ether molecules, they have less room to solvate this lithium. So in other words, you have a lithium compound which is not solvated, and if it is not solvated, it's very reactive. So for this reason, this lithium compound is not behaving so well, but still, when you quench it with dimethyl disulfide, you get 90 to 10. The other one is perfect. You get 90% yield, and the trans ratio is even better. This was our first experiment, it's even 99 to 1. The proof is, oops, I touched something else. Here is, you see, look at this one. This is trans. You have a oxygen function in para position, doesn't disturb. It's trans, and you see you get trans 2 to 98 and 1 to 99. And the cis one behaves a little bit more tricky, but still you get 92 to 8, 94 to 6. So you can make them stereoselectively. But the most interesting thing is that you can extend this to open chain system. So Koei, a student from Japan, he found that if you take such iodide, either the syn compound or the anti-compound, purity, the purity is the 98 to 2, 97 to 3, and if you make the lithium compound, it is stereoselective, and you can then get a quenching with dimethyl disulfide. The formation of the lithium compound occurs with retention, and the quenching also with retention. And you can form carbon-phosphorus bond, but you can also form carbon-carbon bond by using this bi-rep amide. And you can say this oxygen here in position 4 plays a role of coordination. No, it is not the case, because you can take a system with just having a phenyl group, and you get with one diastereomer 98 to 2, you get the same kind of selectivity. You see, for example, even if you have a TBS group here in this position, 98 to 2, you do, for example, a thiomethylation, you get 94 to 6, and if you take the other diastereomer, you get the other one. So, now you see that it's possible with this iodine-lithium exchange to prepare lithium compound, secondary lithium compound in open chain system stereoselectively. I want just on the last slide show you that it has even more potential, because lithium compounds are nice, but lithium compounds, you know, is like when you compare it to weapon, it would be the atomic bomb of the organic reagent, because the bond is so ionic, you get so high reactivity in there that it's difficult to control. You would much better to use zinc or copper compound. And here is the last experiment of Kohei. He showed that you can take this zinc compound, this lithium compound, and convert them to the zinc reagent, and convert them to the copper compound, and do alylation, for example, and the diastereoselectivity is very good. Why were we afraid that this would not be? Because we were afraid from reports in the literature that electron transfer reaction may complicate this system. But no. And you know, even if you start with the trans, we start with the cis, you make the lithium compound, then you transmetallate in ether, minus 100 degrees, and you add copper cyanide, then you get, for the trans it's perfect, 1991. For the cis, you lose a little bit, because this cis reagent has a high tendency to isomerize, as I showed you, but still you get the cis compound 86% to 14. And so, I hope that I have shown you that this lithium chemistry, by using iodine-lithium exchange, may be quite useful for introducing stereo centers in cyclic and acyclic system. Also, I hope that I have convinced you that zinc, magnesium, although they are the first elements almost besides sodium, the Wurtz reaction, introduced in organic synthesis, they still have a lot of potential, and it's a lot of fun to examine the reactivity of all these species. Now, of course, I am not so fortunate to be in the lab each day. Maybe it's better like this. My students, they do all the experiments. They are very dedicated. They have a good feeling of chemistry, of solvents effect and the salts effect and so on. Here they have not their lab coat. This is just, it's also a coat for going to the Oktoberfest, which is a kind of beer festival. And I would like to thank them for their great dedication and hard work. And I would like to thank you again, Scott, for the invitation to come here, and thank you for your attention.
That was wonderful. Okay, as before, we will have a question and answer period. So if you'd like to step up to the mics, either end or the balcony, I'm sure Paul would be happy to answer some questions. And it looks like over there to my left.
Hi, Professor Knochel. It's Chris Thomas, Sigma Aldrich. It's a very beautiful work.
Yes.
So to go back to your zinc pivalate complexes, have you tried making those with just benzene, or is functionality required on the ring for the metallation?
What do you mean benzene?
Well, if you just made benzene zinc pivalate as an interstable zinc.
Just with a phenyl ring, you mean?
Mm-hmm.
Yeah, this is no problem at all.
Okay.
Yeah.
That's all I had. Thank you.
Again, over there.
Yeah, hi, Rob Milichko, Michigan State. So I was curious about the reaction where, because of the magnesium salts, you were able to get the carbonyl addition, and then when you did the cross-coupling, it seemed to completely shut down. At least as presented, both reaction times were exactly the same, and the yields were excellent in both cases. And it made me wonder, is in the cross-coupling reaction, is there something perhaps in the spent byproducts, something that's actually also slowing down the carbonyl addition, or is it simply that you've got just enough rate enhancement? Because again, the reaction times were identical.
I think the palladium cross-coupling is very, very fast. This effect, you know, this nice effect when you have a aromatic bromide with an amide function, and you add a zinc compound. If you have no palladium, of course the amide will be deprotonated. The amide function is relatively acidic, and a zinc reagent, an alkyl aryl zinc compound, would do the deprotonation. But if you have the palladium catalyst, you have this oxidative addition, especially with Pepsi or S-Phos from Steve Buchwald. You have a very fast insertion. And then you form this aryl palladium, the transmetallation, zinc compound transmetallate instantaneously. And so you get the diaryl palladium, and then you get the coupling. And the NH deprotonation is just too slow. It's just a problem of kinetics. Yeah.
Peter Way from Pittsburgh. Do you ever see a trend in your lithium-rich zinc and magnesium reagent to do halogen-dense reactions? Have you looked into that?
Yes. Halogen dense, this is again, halogen dense occurs mostly when you have lithium compounds. And if you have magnesium compounds, it's much, much slower. And with zinc, never happens. Never happens. Because the carbon-zinc bond, that is also an interesting point. The carbon-zinc bond, on one side, it is very covalent, but exchanges very rapidly. So, for example, if you take an aryl zinc and another aryl zinc, the aryl groups are going from one zinc to the other. We check this by marking in collaboration with Konrad Korzinowski in Göttingen. We used marked zinc compound, isotopically different zinc compound, and they exchange very, very fast. But the halogen dense type reaction you do not observe.
In spite of lots of lithium chloride, you never see that.
Yeah, the lithium chloride is a solubilization agent, but also it is the chloride anion coordinates to the metal.
That's an 8 complex.
And makes the 8 complex. And so it enhances the reactivity. And sometimes it's better not to have the lithium. It happens in some exchanges. It's better not to have the lithium chloride, not because of the rate of exchange. The problem is not the rate of exchange. With lithium chloride, it's perfect. But the product that you get, then you get a magnesium compound activated by lithium chloride. By the way, if you have any Grignard reagent and you're not satisfied by its reactivity, you just add lithium chloride, you make the 8 species and it gets more reactive.
Jin Kuan Yu from Scripps. Yeah, you a very nice talk, by the way. You mentioned you can use the zinc reagent at room temperature, at least in Munich, which is pretty stable. Yeah. But what about the thermal stability? What is the higher temperature can you go up to?
The what stability?
The thermal stability of your zinc reagent.
The thermal. Oh, that is excellent also. 120 degrees. We did reaction with organozinc compound in NMP. At 120 degrees, no decomposition occurs.
That's great.
So it's very, zinc compounds are, in many cases we use for this carbo magnesiation, intramolecular carbomagnesiation, we use microwave 50 degrees is not problem at all, 60 degrees is not a problem. And the metallation, when you use TMP zinc chloride,
that was with air, 100 degrees with air?
No, not with air. This I would not do. No. No air.
Okay, with that, I think we'll conclude our morning session. Let's thank our speakers.